I think more than that, I don't need to tell. Mariana, if you are ready, the stage is yours. And in the meantime, you can welcome her.
Thank you very much for the wonderful introduction. It's an unbelievable honor to be here. I titled it On the Shoulders of Building Masters, mostly because, unfortunately for me, or well, I need to get used to the microphone as well, just like you. I was not as fortunate to meet the great heroes such as Frei, Otto, or others from the past, and have such a direct connection in terms of having seen them in person or experienced that in person. Nonetheless, I have had the privilege of experiencing their legacy, their understanding, their systems, and all of their knowledge through masters that are actually present here today, and on whose shoulders I believe I have the privilege to stand. Now, that's not only because of the great work being done in Stuttgart that's been incredibly inspiring for me from the moment that I was studying, but also because of the heritage of having been, of course, at the ETH, at the Block Research Group, that also looks quite often towards the great builders of the past and taking inspiration from that. So in some sense, I try to find myself building on that heritage somewhere at the intersection of architecture, structure, computation, and fabrication, trying to learn from those great masters, not only of the past, but also of today. And I will be a little bit more zoomed in trying to explain a system that I've been working with and developing, built on these kind of principles. I don't know if it is the future or the answer to the future, but I hope that answers in terms of systems or methods can be found within it, and not necessarily only the specific geometries. I like to look at things very much from the perspective of geometry. One being the global geometry, which is generally considered either being the architectural geometry or the structurally informed geometry. Now, I don't find those mutually exclusive. I just put them explicitly there because they could be different. And of course, because of my academic upbringing, I believe very much in the structurally informed geometry in that sense, that I believe everybody here through form finding methods and other methods also believes in. On the other hand, I try to go to the other side and look at the local geometry or the material system, or how we could place material only specifically where we need it so that we can be as effective as possible with it, not only in global terms, but also in local terms. And this is very much afforded by the types of digital technologies that we have today, both in terms of design and fabrication, that maybe were a little bit more difficult in the past. So in that sense, I'm hoping in very many ways to think of the design, fabrication, and building process as a loop that informs each other, rather than a linear process where we start with a design, we engineer it, we fabricate it, and we construct it, and we try to find out at every step of the way how the structure or the equilibrium could deal with the material and so on. Very specifically, I did most of the things I will show you are an homage to some great builder from the past and are named that way as well. It started with actually trying to understand how we might build efficient forms that span large space with very little material, are usually complex in their geometries, and very often made in concrete. And this is also, of course, one of the legacies of having been at ETH that deals with concrete, or Switzerland that deals with concrete quite a lot. What we look at generally when we look at these kind of efficient forms is that they use very little material, but when we build them, we're not quite as efficient. So the hope there was to try and go towards a way of building them that might be less materially intensive. And in that sense, developing a fabric formwork system, and that is absolutely not new. That is something that people have been trying to develop for the past more than a century. But what I specifically look at is how you could do that with a knitted membrane, a 3D knitted membrane. So the reasons for that is because you can actually have these kind of very local tailored material properties that you can put material where you want it. It can be lightweight, it can be used with minimal intrusion, and it could serve as a formwork. The way this works is usually by starting with a design, hopefully a structurally informed design, using existing machinery to knit tailored textiles that represent that design or get to that geometry. Then that textile, as we know from everything that is around us, needs to be somehow tensioned into shape. This could be done in various ways. You could do it with an external frame, you could do it with inflatables, you could do it with cables, you could do it with all sorts of, with any way that you can think of tensioning a textile into shape. And then it is coated with a thin cement-based coating or other type of coating to give it an initial rigidity. And the reason for that is because usually they are incredibly deformable. So if you were to cast directly into it, it would deform so much that you wouldn't get to the geometry that you want. And getting to that geometry is part of the quest. Now that becomes the formwork for concrete, where you can cast normally. And the first or the largest prototype showing this method is the knit candela. But before that, actually, there are two difficult parts to this, or two challenges. On the one hand, how do we get from the design to the fabrication side of things? So if I have a geometry, how do I get the files for production? And those are dealt with through computational pipelines. And if we do have that textile, how do we actually build with it? On the building side of things, as I was saying before, we started with a prototype that is named Knit Candela, an homage to Felix Candela, looking at inspired by the geometries in Mexico City at Xochimilco, where we tried to realize this type of complex geometry that is not based necessarily on hypars or ruled surfaces, but is a doubly curved geometry, and is actually also a waffle shell. So it has rib stiffener. It's a thin concrete shell with thin rib stiffeners in two directions. Of course, this starts with a form finding exercise with a force density method and so on. For that, we generate a pattern for a textile. We produce that textile and take it very compactly in 2 suitcases on site, where it can be spanned in an existing rig to create the formwork. Now, I love this photo, and actually the person that took this photo is right here in the audience, and it is one of the photos that I show the most, because it is it shows how lightweight and transparent such a formwork can be, both because you can see the light through it, but also because it doesn't have a lot of supports. And also it shows a face of relief that this actually worked, that it did stretch to the size that it needed to, which we weren't completely sure before it actually did. You'll see the next step is one of coating it with a very specially designed thin cement paste layer. And you'll see Lex Reiter, who was my colleague at the time, who developed the recipe for said thin cement-based coating, applying it very precariously, hanging from a scaffold. And what is left on the other side is kind of this array of cassettes that become the cavities within the concrete. Now, on this, you can just cast concrete normally. And once that concrete is hardened, you can take all of the frames away and you'll end up with a structure like this. I spend a lot of time on this, although it's a project that is a while ago, because it is one of the projects where you can see that this method can indeed be used to construct concrete structures. And some of the implications of the project are that it cost about 2,500 euros for 50 square meters of textiles and cables that make the formwork. It only weighed 25 kilos. It took 36 hours to produce on the machine. And usually it takes about 750 hours to mill 50 square meters of doubly curved surface out of foam. And in total, it took about 14 weeks to get from the design to the standing structure there. Of course, the 14 weeks don't take into account 2 years of development before, but once you have it, you have 14 weeks to go with it. And one of the key enablers there are the computational pipelines. So the part of how do we get from a design to instructions for the machine? Because usually these types of machines are used for our clothes, and we do these types of things manually. So, of course, having this kind of computational pipeline that translates that design is one of the key enablers. it is interesting also for the knitting machine manufacturers in that sense, because it opens up a new sector for them. And this is one place where the relevance of whether these are the types of structures specifically as geometries, I don't know, but perhaps the types of pipelines are something that can have a broader impact within the industry. The next prototype that I will not spend as much time on as the previous one, because it does show the same kind of principle, is called Knit Nervi, because it is an homage to Pierluigi Nervi in this case. We are reimagining that kind of geometry that they did with rib stiffeners in two directions for the Palazzetto dello Sport. And very conveniently, it was also built a couple of 100 meters from where this structure stands at the Maxi Museum in Rome. And here we tried to minimize as much as possible the extra scaffolding that you might have, but also look at how we could have a structure where the reinforcement is actually integrated within the structure itself as a support for the fabric formwork. This, of course, is done with the same types of methods of graphic statics and form finding in that sense to get to a geometry that echoes a little bit of the types of geometries that you see in Stuttgart, and that is also because part of the team members were educated here in Stuttgart, so that comes with this kind of legacy. What we did is we created a bending active grid shell made out of rebar. That bending active grid shell is held up on normal props that you can reuse, and we created the textile fabric formwork around it that actually is held up by the rebar. In this case, we actually look a little bit closer between that global and local geometry, specifically because if you look between the rib stiffeners that are transparent, you'll see that there are very gradient-like textures in between. So at this point, actually, those computational pipelines for generating these patterns need to be developed both to make a larger structure, because this is twice the surface area of the previous one, though it may not look it, but also control those very specific material properties locally. And in that sense, creating these kind of algorithms that can take a 3D geometry, represent it as an algorithm for the machine, but also post-process it as instructions that go directly to the machine to be manufactured are very important. Finally, when the structure is there, you end up with something like this. And it shows this kind of connection between being able to have these efficient deployable structures, being able to have graded material properties, which we can both design with computational design tools, but also these computational fabrication pipelines. That computational fabrication pipeline was then taken into the next project, which I will show very briefly because it has a connection to what the students have been doing as part of my visit here. We built a purely bending active, so this was not supposed to be a grid shell or a formwork for concrete, but together with Soil, which is an architecture company from the US, we built a pavilion for the Bruges Triennale, where you kind of inconspicuously go through this garage door and down the rabbit hole, and you get flipped inside out through this textile and kind of weave through that space there. And it's very much inspired by the lace making tradition in Bruges, and we tried to translate that into the patterns of the structure that we had there. I will not go into the details of it, but I wanted to show it because what we did is we looked at this as a temporary structure and started also asking, well, how might we demount it and what might we do with these kind of temporary structures once they need to go away? And what we did do is take the textile from the structure and bring it to Stuttgart to work with students here on creating something new out of it, touching upon ideas of circularity and reuse. And you'll see more about that from them. And finally, in the last minute that I have, I wanted to share the last one, which is actually probably the most related to Frei Otto in that sense, because during the period that I had the privilege of being in this tent in November, December last year, we started working on a project for the Venice Biennale with the same architects as before. And it is called Necto, but I had proposed, and I would still propose secretly, that the title of this work is Notto, as in Knit Otto. Because you will see a lot of inspirations from the types of geometry and the types of expression that you can see around the tent. And I can only say that it probably had a massive influence during this time that we were developing it, to be in this tent and look around, look at models, see different things. Now, and I'll show a few geometries of it. You'll see a few again features that we've seen also before, this kind of eyelet, this kind of drop. But we also wanted to think of it as a form finding exercise that is instructive for the people. So you'll see also these kind of weights here that show you how to work with the form finding process. A little bit of an echo of what has been done in the models here. Very specifically, and I will not take more than 1 minute to finish this. What we did in this case, we looked at the membrane, and we also aligned the fabrication patterns with the principal stresses within the membrane, with the two principal stresses. On the one hand, that was one way to discretize the different patches that the membrane would be made in. And on the other hand, they were used to have flex as inlays, which would become the structural components within this membrane. They are visualized as stresses in two directions. On the one hand, within the texture of the textile, and on the other hand, with the flax fiber inlays, which give it a little bit more structure. So, in conclusion, if we can have efficient, flexible formworks, and we can have graded materials, we can have adaptive hybrid systems through the way they're built, and we can have automated fabrication. What we have there are a few hinges of computational design and computational fabrication pipelines. But what's very interesting for me right now is actually this corner, where we crucially need to somehow understand what the material properties are of these types of materials. And in that sense, all of our computational tools have not made it that we don't model anymore. We still need to understand these systems through physical prototypes, because with knits we have a lot of different opportunities, and we can have these kind of graded material properties, but we still struggle to understand them actually very much as they were being understood 50 years ago through physical testing. And with that, I would like to thank you very much.